So with my students in my Regents Physics class, we've been doing a bunch of review. We've been looking at multiple choice questions from 2002 when they changed the exam to 2013, the last exam. There have been 966 questions. I've given my students about 300 of them, although not every student had to do all those questions. But I did a bunch of analysis, and these are the 40 most missed questions for my students. And I noticed two big patterns. One of them was vectors. When it comes to adding vectors, getting components, there's some confusion there. And the second are energy problems, specifically energy problems that deal with internal energy, or Q. So what I'm going to do is I'm going to go through each of these questions. I'll pause for 3-4 seconds, let somebody read it, then I'll circle the answer, and then I'll go through a little bit of an explanation. So if you want to skip, feel free. Question number 1. You have to remember that sound is a longitudinal wave. Remember, waves can be mechanical, they can be electromagnetic. Mechanical waves need a physical medium, and sound waves are a type of mechanical waves called longitudinal. They're compression waves. So there's an area of compression, and then rarefaction, and then compression. These areas, these compressions are kind of like the crests in a transverse wave. So when I speak to you, the air is being squished, and then it stretches out and it squishes. That vibration is parallel to the direction of movement. So if the wave is moving east, that means the vibrations are also going to be east and west. Question 2. The answer's 4. Now, this is a sort of vector question. Remember, when you add vectors, these two vectors are the same as long as they keep the same magnitude, length, and direction. It doesn't matter how you draw them. If I was to draw and I want to add these two vectors, one way to do that is called the parallelogram method, like this. Finish off the parallelogram, and then this will be the resultant. The other way would be to do the head-to-tail method. So if I take this vector over here and I move its tail to the head of the first vector, like so, the resultant is from the tail of the first one to the head of the last one, like this. This is the resultant. Either way, you're going to get the same thing. It's just how you think about it. Now, at this point, this is a right triangle, and all x and y components are. A squared plus b squared equals c squared. So that's 400 plus 400, square root of 800. I'll skip that. People are usually good at this. You should get 28 newtons. That part people were good with. What they got wrong was the direction. Most people said northeast, and they correctly added the vectors, but you have to read the question. It says, what additional force is necessary to bring the object into equilibrium? In other words, what's the equilibrant? They don't want R. What they want is this, the equilibrant. The same magnitude, just the exact opposite direction. So it is 28 newtons, it's just that it's 28 newtons to the southwest. Let me just make sure this is still going. We're good. For the third question, by the way, these questions go in the order from most missed to least missed. This is an energy question. Look on your reference table. I've copied and pasted it for convenience, but I strongly encourage you as you're studying to have that out. There's a mental association with knowing where things are. There are two definitions of work. Work, on the one hand, people are used to being force times distance. That's not going to help us here. The other definition of work is that work is the change in the total energy. Now, the total energy is potential plus kinetic, and if there's any internal energy. In this case, because it's a horizontal table, and that doesn't change, there is no change in potential energy. In other words, all of the work that we're doing is going into the kinetic energy. So to solve for the work is the same thing as finding for the change in the kinetic energy. So that's going to be the final kinetic energy minus the initial kinetic energy. So that's going to be 1/2 mvi squared plus, or minus, let's make this final minus initial, minus 1/2 mvi squared. So that's 1/2 m times vf squared minus vi squared. 1/2 times 15 kilograms. Now that's 11.5 meters per second squared minus 7.5 meters per second squared, and you should get 570 joules when you do that. Question 4 is 1. Now, I think when people see this temperature, they think the question's more complicated than it is. The fact that the temperature stays the same is just letting you know that the resistance stays the same. The warmer it is, the higher the resistance, but this is just a straight Ohm's law question. R equals V over I. So if you increase the voltage and the resistance stays the same, then the current will go up. In fact, it's a linear relationship. V equals I R. If you double the voltage, you'll double the current because the resistance stays exactly the same. So the only thing that's increasing here is the current. Question 5. The answer to 5 is 1. Now, this is an energy problem. This one always gives people fits. We have here a change in potential energy because you're raising it here, and that amount of work that you put in is somewhat more. So you're putting in 400 joules of energy, but the change in the potential energy is going to be somewhat less. We need to figure out how much less. Again, work is the change in the total energy, which is going to be the change in the potential plus the change in the kinetic plus any internal energy due to non-conservative work, basically friction. Now, the potential energy is changing. That's mgh. The kinetic energy is not changing. It's stopped in the beginning, and in the end it's stopped. So there's no change in kinetic. We want to know the internal energy, and we're told that this was 400 joules of work that we put in. Now, instead of giving us the mass, they actually give us the weight force, and I think that throws some people off. Remember, weight equals mg. It's almost like they're saving you some work, or probably poor choice of word, saving you some effort. So 72 newtons is mg. And the h, the change in height, is 5 meters plus q. So 400 equals, let's see, 360 plus q. Notice if this was a part 2 B2C question, I plugged in with the units here. We don't have to keep using the units here. It's not bad to do that, but you don't have to. And when you solve 400 minus 360, you're going to get a Q of 40 joules. In other words, when you raise this by pulling on the rope, you put in 400 joules of energy. 360 of that went into the potential energy from being raised higher, and 40 joules of that went into heat, into friction with the pulley and such. 6. The answer is 3. Very similar to before, the tuning fork produces a sound wave. Sound waves are mechanical waves, and specifically, they are longitudinal waves. They're compression waves. Same as before. They're longitudinal because the vibrations are this way. This piece will still never move over to here. It just wiggles back and forth, but the direction of that motion is still in the same direction as the propagation. 7. The answer is 2. Now, this is actually a straightforward wave question here. V equals F lambda. STP sometimes scares people, but when you look on the first page of the reference table, you'll get the velocity of sound in air. So you just plug in the velocity, 331 meters per second equals the frequency, 512 hertz, times the wavelength, and you divide, and you will get the wavelength, 0.646. Question 8. The answer is 2. This is a really good question. I like to call this a numberless question. When you see this kind of question where it's graphing or patterns or this doubles or this or triples, what happens to something else, I strongly encourage you to think about what's the equation. Well, the equation here, which I guess I didn't put there, we'll just write it, but R equals rho L over A. This is the resistance of a wire. It depends on the length, the area, and the resistivity, a property of the material. So then you say, well, what are the two variables that are changing? R and A. So I rewrite this with everything else as a 1, and you're left with R equals 1 over A. That kind of relationship is a 1 over R, or an inverse relationship. By the way, I think I circled the wrong answer, didn't I? Oh yeah, the answer is 4. But it's a 1 over R relationship, which is choice 4. Now, I noticed that a lot of people picked this, I think because they mix up a negative slope with inverse. They're not the same thing. This is still a linear equation, y equals mx plus b. It just happens to have a negative slope. But it's still linear. It's just a negative linear. So the answer here to number 8 is 4. 9. This is a modern physics question. The answer is 3. Now I have to admit, I had to read it a couple times. It's very wordy. I had to think about it. It's worth noting that UDD, first of all, remember the kinds of particles we have in matter. Everything's either a lepton, which is one of those 6 particles, or you're made of quarks. If you're made of quarks, you're a hadron. If you're made of 3 quarks, you're a baryon. If you're made of 2 quarks, you're a meson. Back to the problem. You have neutron decay, and you're told that a neutron has the quarks U, D, D. And you're told a proton is U, UD. These aren't the kind of things you would have memorized. I certainly don't. But in going from here to here, notice this is made of 3 quarks and this is made of 3 quarks. So you're going from baryon to baryon. That's why that's the answer. But we can actually rule out the other ones. Lepton to lepton. Well, neutrons and protons are made of quarks. They're not leptons, so it can't be that. A D quark to a meson. Well, yeah, we're down 1 D quark, but it didn't turn into a meson, so that doesn't make sense. And a U quark to a D quark. This is probably the most devious because we do change a quark, but it goes from D to U, not U to D. So that's not that one. So the answer is 3. Question 10. The answer is 4. Now, you can do this with really any of the energy equations. Let's try kinetic energy. Kinetic energy equals 1/2 mv squared. We only care about the units right now, so I'm going to ignore the half. Mass is kilograms. Velocity is meters per second, and we're going to square that. So you're left with kilogram meters squared per second squared, which is our answer. Worth noting, we can do this with any of the energy equations. If we'd have done this with potential energy, the gravitational potential energy would be mgh. That would be, again, kilograms meters per second squared times meters. Either way, you wind up with the same thing. 11. The answer is 270. Oops, don't want to do that. This is really the same kind of concept we did earlier. You have an object that weighs 40 newtons. It's going to slide down that ramp, and if there was no friction, all of that potential energy in the beginning would turn into kinetic energy because there'd be no potential and there'd be no work non-conservative. So energy total equals potential plus kinetic plus any internal energy. So at the top, we have the potential, which again is mgh. There's no kinetic, there's no internal energy. And again, instead of giving us the mass and multiplying it by g 9.81, they give us this, which is essentially mg, the weight force. So we can plug that in directly, 40 newtons times 8 meters. And we can see that in the beginning, we have a total energy of 320 joules. When we get to the bottom, you're told that you lost 50 joules to heat. So if you have 320 joules and you lose 50 joules, that gives you an energy at the bottom, a total energy of 270 joules. 12. 2. As it passes through a slit, the diffraction depends on the relative size of the wavelength to the opening. So let's say this is the opening. If you have waves that are pretty close in wavelength to the size of the opening, you're going to get it diffracting or spreading out quite a bit. Whereas if we had openings like this and we had the same waves, it's still going to diffract, but not as much. It's much straighter. So closer the wavelength is to the slit size opening, the more diffraction you're going to get. 13. Thirteen is one of those questions where I think we confuse ourselves more than necessary. When you have a magnetic field line, much like an electric field line, it tells you the direction the north end of a compass would point. So a compass is always going to point in the direction of the magnetic field lines. So the answer is going to be 2. Now, I think I know why a lot of people pick the exact opposite of that, choice 1, and I think it has to do with the Earth. This is the Earth. This is the Earth's geographic North Pole, where Santa Claus lives. This is the South Pole, where the penguins live. And the magnetic field actually, instead of going from the North Pole to the South Pole, goes from the south to the north, because this is actually a magnetic South Pole and a magnetic North Pole. I know, confusing, right? So the North Pole on a bar magnet actually points towards the south magnetic pole of the Earth, which is the north geographic pole. Sorry for the confusion. $14. It's going to be a very long video. The answer to 14 is 1. As for why this is momentum, this is a conservation of momentum problem. So if you're going to solve this, if this was part B2C, you'd write the initial momentum equals the final momentum. And then you're going to do the momentum P equals mv for all of the little pieces. So in the beginning, we have one little m, so I'll call it mass of the clay, times the velocity of the clay plus the mass of the block times the velocity of the block is going to equal. And afterwards, this is an inelastic collision. They're going to stick together. So you're going to have one mass, which is the mass of the clay, plus the mass of the block, and it's going to have some velocity afterwards. We're asked to solve for that velocity. Well, the velocity of the block before is 0, so this is just 0. And this is 1 kilogram, and this is 6 meters per second. So together that's going to be 1 kilogram plus 3 kilograms times the velocity prime. So you wind up with 6 equals 4v prime, or v prime equals 1.5 meters per second. But conservation of momentum, very important problem. By the way, the other kinds of conservation momentum problems might be something called an elastic collision. It's the same principle, there'll just be two objects afterwards. And an explosion. Again, the same principle, but there'll be one object before with the total momentum of 0, and afterwards there'll be 2 or more pieces. And their momentums are still going to add up to the total momentum. So whenever you have a collision, the momentum of the pieces changes, but the momentum of the whole system stays exactly the same. It's a big idea. 15. The answer is 1. I can't tell you how many years people ask me what the word concurrently means. Concurrently means at the same time. You can basically ignore that question. Really, when you have two forces, this is a vector question. Those vectors, when you add them, and this comes up again and again in this problem set, I noticed you guys struggled with this. When you have two vectors, let's say they're two 20-Newton vectors, the biggest magnitude you can get is when they're facing the same direction. In other words, when the angle between them is 0 degrees. So if this is 20 newtons and this is 20 newtons, that is going to give you 40 newtons. As long as we're here, if I added 20 newtons plus 20 newtons in the other direction, that is going to give you 0. If we had 20 newtons and 20 newtons this way, it's going to give you something in between. Now we happen to know, because we did this in one of the first questions, it's actually going to be 28, Pythagorean theorem. But the point is, the biggest you can get is when the angle between the two vectors is 0 degrees. The smallest you can get is when the angle between the two vectors is 180 degrees. Everywhere else is somewhere in between. Question 16. The answer is 3. Now, I like this question. There's two ways you can answer it. One is with an equation. Acceleration is change in velocity over time. So when you're going from 8 meters per second to 16 meters per second in 10 seconds, that gives you an acceleration of 0.8 meters per second squared. But we're not done yet. They want to know how far it goes, and then you can use the d equals vit equation. By the way, here are the equations. Page 6, 50% of the exam. Look at it. When you plug in your numbers there, and I'm going to just save some time there, you will get 120. Now, you could also look at this graphically. Let's say I had a graph like this, and this is velocity and time. A big idea is that the area of a graph means something. If I take the velocity times the time, that is going to give me displacement. Now graphically, if this is 8 meters per second, and this is 16 meters per second, and this is 10 seconds, the graph of the motion, the velocity time graph, is going to look like that. And it can be broken up to get its area into this rectangle. 8 times 10 gives me 80, and this height, 1/2 base times height, 8 times 10, this square is 80, so half of the square of the triangle is 40. That's going to give you 120 meters. So either way you do that, that's the answer you're going to get. And this came up several times in this problem set. 17. The answer is 1. It's going to decrease. And again, this is sort of like a vector problem. As the force vector, as the angle gets bigger, like if this was the force vector this way, there would be no part of this vector that's sideways. There would be no acceleration. If we had the force vector this way, all of that x component would be the same size as the overall magnitude. In other words, it would be, the x component would be as big as it can ever get. In fact, the x component is always going to be the magnitude times the cosine of the angle. And cosine of 0 is 1, cosine of 90 is 0. So as we increase theta, say something like this, it's just going to be a little baby x component. Fx is going to be very small. Fy is going to be very big, but that's not going to do anything to accelerate it horizontally. So as theta gets bigger, as it goes like this, the x component gets smaller, so the force horizontal gets smaller, and A equals F over M. If F gets smaller, A gets smaller. 18. Now, in full disclosure, there was a typo. This is supposed to be meters per second squared. But as far as how you do this, A equals F net over M, or F net equals MA. That's kilograms meters per second squared. So if you divide a Newton, which is this, by the way, unit for force, by kilograms, then the kilograms go away, and you're left with meters per second squared. 19. The answer is 1. Again, you can answer this one of two ways. You can use the constant acceleration equations, or the area on a VT graph, or speed versus time graph, velocity times time, is displacement. So for the first 3 seconds, you're going to go to here. This area is going to give you the displacement. That's 1/2 base times height. That's 1/2 times 3 seconds times 8 meters per second. That's going to give you 12 meters. Or the way I mentally think about it is 8 times 3 gives me 24, and a triangle is half of a rectangle, so it's going to be 12. 20. The answer is 4. The equation you can use here, and one people don't always think about, is this one right here. Power is force times velocity. Yes, power is work divided by time, so it's force divided by velocity, divided by time, and displacement divided by time is velocity. So this is actually very straightforward. Power equals force times velocity. One thing, though, is that the weight is irrelevant. The force you use is 600 newtons. The velocity is 15 meters per second. You plug that in, and you will get 9,000 joules. Or, I'm sorry, 9,000 watts. By the way, that's a joule per second, which is the same thing as a watt. 21. Basically the same discussion we had a few minutes ago. You have a 5 Newton vector and a 7 Newton vector. Their magnitude will be the biggest, head to tail, when they are in the same direction. In other words, when the angle between them is 0 degrees, that will be the biggest. That will give you 12 newtons. The smallest you can get is if you have 5 newtons in one direction and 7 newtons in the exact opposite direction. In other words, when the angle between the two vectors is 180 degrees. So 7 minus 5 is going to give you 2 newtons. So by the way, this will be 12 newtons this way. This will be 2 newtons that way. So since we're going from 0, where they have the biggest magnitude, to 180, where they have the smallest, we're going from 12 newtons to 2 newtons. 22. Again, this is the same concept. This is our third time hitting it. The area on a VT graph, rather, speed versus time, is displacement. So during the first 4 seconds, that's this. That's 1/2 of 20 meters per second times 4 seconds. That's 1/2 of 80 meters. That's 40 meters. The answer is 40. It's the area on the VT graph. 23. The answer is B. Now this is a vector question, a vector addition question, but it's a little bit different. Instead of giving you the two vectors and saying add them, they give you one of the vectors and the resultant and find the other. It's like saying 2 plus x equals 5. Instead of giving you 2 plus 3 and solving for 5, they're giving you 2 and they're giving you 5 and asking you to solve for x. So if this is the resultant, A, let me just erase this. I'm going to redraw it over here. So something plus that has to equal the resultant. Well, that something has to end, if I'm drawing the head to tail method, like this, and it has to start here, so it's going to be this vector. It's going to be number 1. Again, head to tail method. When you add vectors, if you want to add this plus this, that would be this plus this, and that would be the resultant. Or sometimes, and more confusing for students, there'll be a vector that, say, looks like this, and then one that looks like this, and they'll say, draw the resultant. Well, one way to do that is the parallelogram method. So imagine that you were drawing this is parallel to this, and this is parallel to this. The resultant is going to go from the base where the two vectors meet in the tails to the opposite corner. Either way, you'll get the same resultant. But vectors are definitely something that we need to work on. 24, again, same concept. Concurrently just means at the same time. You can basically ignore it. When the two vectors are 0 degrees apart, their magnitude will be the biggest. When it's 180, it will be the smallest. So read the question. They want to know when the largest magnitude is. That's when the angle in between them is 0 degrees. 25. We answered essentially this same question, but we had numbers earlier. This question just doesn't have any numbers, but that's the same. The answer to number 25 is 4. And the reason is exactly the same. PI equals PF. And we're going to apply P equals MV to the pieces. Before you have two pieces. You have MA, you have MB, and afterwards you have MA plus MB, because they stick together in an inelastic collision, times the velocity of the blob afterwards. The velocity of B before is 0 meters per second, so now we're just leaving it in terms of variables. So MAVA equals MA plus MB times velocity prime, the velocity of the blob after the collision. You want to get V prime by itself, you just divide. V prime equals MA over MA plus MB times the velocity before. Look at our choices. That's choice 4. 26. This is one of those questions where I think it's only hard because of the graph. The concept's relatively straightforward. It's an energy question. Constant speed. Because it's constant speed, the velocity's not changing, so the kinetic energy is a constant. And the fact that you're pushing it horizontally across a level wooden floor tells you that the potential energy is also constant. So what's going on? The person is still doing work, but none of that work is going into the potential of the kinetic. It's all going in internal energy. The box is heating up. But in terms of total mechanical energy is the potential plus the kinetic. And since it's not going faster and it's not getting higher, it's exactly the same. Graphically, the line that means exactly the same is this, number 1. So 27. The answer to 27 is 3. There's no math necessary here. The force on one object is the same as the force on the other. The fact that they're planets is irrelevant. This is the same kind of question as you're sitting at a traffic light in a very small car and a tractor-trailer rear-ends you. Who feels the bigger force? You feel exactly the same force. Now, the effects may be different. The acceleration is different because you have different masses. But the forces are exactly the same. You can't touch without being touched, and as hard as you hit something, it hits you back just as hard. Here you have the Earth and the Moon. This is Newton's third law. They pull equally hard on one another. Every force is actually an interaction between the two objects. 28. The answer to 28 is 3. Now this is a question again about vector addition. And you want to think about the resultant for each of them. You want to know which of them could have a resultance of 30 newtons. Well, remember, if you have an x component and a y component, the resultant is going to be bigger than either of those. You can get it with the Pythagorean theorem, but it's going to be bigger. The reason we're making a big deal of that is see how this has an x component of this vector, kind of like this, almost as big there. You're definitely going to get something much bigger than 30. So that can't be it. In question 2, that x component is smaller, so it won't be as much bigger than 30, but it's still going to be bigger than 30. In question 4, 30 newtons to the right, 30 newtons to the left, that is going to be 0. So the only possible answer is question 3. But we can actually add this as a vector and sort of prove this to ourselves, and it's not a bad review. So whenever you're adding vectors, you want to think about the x component and the y component. So here, this vector has an x component of 30 newtons and a y component of 0 newtons. And this vector, we're going to break it into its x and y components. Remember, the x component of any vector is equal to the magnitude times the cosine of theta, and the y component is a times the sine of theta. So this is going to be 30 times the cosine of 120 degrees, and this is going to be 30 times the sine of 120 degrees. And when you do that, when you add, let's see, so this, I put in my calculator, this is 15. Yeah, when I add those, I think it must be 15 newtons. So 30 plus whatever 30 the cosine of 120 is gives me 15 newtons, and 0 plus 30 times the sine of 120 gives me 25.98 newtons. So if we were adding these as vectors as a vector addition problem, there would be an x component of 15 newtons plus a y component of 25.98 newtons. Notice how those are always perpendicular. That's the beauty of x and y components. So the resultant here, you do a squared plus b squared equals c squared, and you will get a resultant that is indeed 30 newtons. So it's a very long question, answer to a question, but it's good review. 29. 29, the answer is 2. And there's sort of two ways to think about this. Here's the way I like to think about it. The gravitational force, or the weight force between two objects. I'll call it weight 1. Big G, mass of the Earth, mass of the thing, over the distance squared is the weight force. They give the value for that for 5 different locations for this object. Now, at some other location, they want weight 2 to be 28 newtons. The formula is the same, G, M, E, mass of the thing over the distance to the second thing squared. And I'm going to write it out this way because notice what happens. The g is the same in both cases. The mass of the Earth is exactly the same. And frankly, the mass of the thing is exactly the same. So when I divide by that, you end up with weight 1 over weight 2 equals R2 squared over R1 squared. We want to get what's R2. Well, weight 1 over weight 2 times R1 squared equals R2 squared, or take the square root of both sides, and then you can plug in. Now, 1, 2, what is that? Well, we just need to pick a value. So let's take row number 1. And weight 1 is going to be 1 times 10 to the 3, which is 1,000 newtons. And weight 2 is the desired weight, 28 newtons. R1 squared is going to be 6.37 times 10 to the 6th squared. Take the square root of that. That is going to give you an R2 that is 3.8 times 10 to the 7th meters, which is the answer. Now, I know that was very algebraic. It's a little tough to think about it that way for regions, but you can do it. The alternative is to use just g m1 m2 over r squared and solve for the mass of the thing. And then plug in the mass of the thing into this equation and solve for the distance. So that's the other way you can do that. I know it's a challenging question. The answer to 30 is 3. Students hate this question. They hate this kind of question. I'll tell you right now, this estimation question is typically question 36. Look for it. It's an estimation. One kind of estimation is with weight. Now, little fact you can remember is that 1 Newton is about the weight of an apple. I can also tell you that 1 pound is about 5 newtons, roughly. If you don't remember that, weight force equals mg, right? 1 kilogram. Now permit me to use 10 instead of 9.81 meters per second squared gives you 10 newtons. So 1 kilogram is about 10 newtons. Well, how much is a typical student? Well, typical student is maybe 60 kilograms. 60 kilograms times 10 newtons gives you 600 newtons. But even if you pick something different, these other choices, as they usually are too absurd. 60 newtons, well, at about 5 newtons a pound, that's like 12 pounds. That's way too small. And 6,000 newtons is way too big. That's like 1,200. That's not going to work. So the answer has to be 6. Other common estimation questions are things like centimeters versus millimeters. And this particular estimation question doesn't have scientific notation, but a lot of them do. I encourage you to convert them into regular numbers. 31. The answer is 2. This is just a good old, do you understand the difference between distance and displacement? So let's say you have a base, and you're supposed to go from here to here. Let's say that that's 30 meters. And then you're told you go 3 meters past it. Whoops. You realize the error of your ways, and you go back 3 meters. You have now gone a total distance of 36 meters. Distance is the actual path length traveled. Displacement, however, is your final position minus your initial position. So that is going to be 30 meters because you ended up 30 meters away from where you started. It's your final minus your initial. It's also a vector, has a direction. The odometer in your car is basically like a distance measure. it tells you how far you went. How far you actually went, that is your distance. Where you end up compared to where you started, that's your displacement. I always like to joke around that if your car's odometer was a displacement meter, it would be very depressing because you'd leave your house, go to school, go to work, come back at the end of the day, and you would have nothing to show for it. Your displacement would be 0. But your distance would be much more. Question 32. The answer is 4. This is another energy question. The minimum kinetic energy of the cart. It needs to have at least as much kinetic energy before as you have potential energy afterwards, because the total energy is potential plus kinetic. In the beginning, it's all kinetic, and at the top, it's all potential. So we need to figure out how much kinetic energy it had in the beginning. I should say we need to figure out how much potential energy it would have at the top, and then that'll be the same as the amount of kinetic. So the potential energy equals mgh. It's going to be 5 kilograms, 9.81 meters per second squared, 10 meters, and that is going to give you your answer there. 33. The answer is 4. Now, I think reflection throws people sometimes because we spend so much time talking about refraction and the bending of light at different speeds and different mediums. This is just reflection. Reflection is very simple. The angle that light comes in at is the same as the angle that it leaves at. So if you have a light ray that comes in at 45 degrees, it will be reflected at 45 degrees. Again, you're measuring relative to the normal. If it comes in at a different angle, a little more oblique, it's going to go like that. But the angle in equals the angle out for reflection. 34, again, is a diffraction question. And just like we talked about earlier, by the way, the answer to 34 is 3. Just like we talked about earlier, it's the slit size compared to the wavelength that matters. So if this is the slit, the bigger the wavelength is compared to the slit, in other words, the closer they are in size, the more the diffraction. Whereas if it was like this, it's going to diffract a little bit, but not nearly as much. So a long wavelength and a narrow opening are closest in size, because usually the opening is much smaller than the wavelength. 35. The answer is 2. That throws off a lot of people. It's an energy question. Potential plus kinetic is total, plus any work non-conservative, any internal energy. But some key words here. Constant speed. Because the speed is constant, the kinetic energy is not changing. So the kinetic energy is constant, even though it's going up the hill. You usually think of it as slowing down, and if there wasn't an energy being added by the engine, it would slow down. But because you have the engine to keep adding energy, the kinetic energy is staying constant. Now the potential energy does go up because you are going higher. So as it goes, it increases in kinetic energy. I should say its potential energy increases because it's going higher, but its kinetic energy remains the same. $36. The answer is 3. Again, this is your total energy. On the one hand, your total energy is potential plus kinetic, plus any internal energy, any work non-conservative. You're told that the kinetic energy increases by 300 joules. You're also told that it's a horizontal floor, so even though it doesn't say it explicitly, because it doesn't change height, you know the change in the potential energy is 0. The change in the kinetic is 300. So if this is 0, and this is 300 joules, plus any internal energy, that's going to give you your total energy. It's 300 plus Q. But keep in mind the work. Work is going to be the change in that total energy, 300 plus Q, but it's also going to be force times distance. So you're told that that force is 25 newtons and that the distance, or the displacement, is 30 meters. That is a work of 750 joules. So now 750 joules equals 300 joules plus Q. That Q is 450 joules. In other words, you actually put more energy into the friction, into the heat, than the box gained in terms of kinetic energy. That happens sometimes when there's a lot of friction. 37. The answer is 4. And I was actually a little surprised to see it this far down the list. I thought it'd be one of the top 10. This is one about impulse. You can see over here. An impulse has two definitions. On the one hand, it's force times time, and on the other hand, it's change in momentum. We have both of those in this problem. Change in momentum, which is mass times change in velocity, and it's force times time. Well, the mass is 1,200 kilograms. The change in velocity, it's brought to rest from 10 meters per second, is negative 10 meters per second. The force is what we want to know. Time is 0.1 seconds. Sorry for the squish. And that is going to give you a force that is negative 120,000 newtons, or magnitude of 120,000. In scientific notation, move the decimal over 5 times. That's going to be 1.2 times 10 to the 5 newtons. So that's going to be choice 4. Question 8, or 38 I should say. The answer is 2. Now I actually think most people knew the equation for the force on a spring, Hooke's law. What's different about this question, very different, is when you look at the axes, this is force and this is x, the stretch. And this is the opposite of the way you normally see these graphs. A lot of times when we teach Hooke's law, we say, oh, here's a graph of f, here's a graph of x. What's the meaning of the slope? And the meaning of that slope will be f over x, which is k. But this is the opposite. So you can't just go taking the slope of this to get the spring constant. Now, you could take the slope and then take the inverse of it, or what I suspect most people would do would be to just take a value of it. So for A, you have a lot less force to get the same stretch. B, it takes a lot more force to get the same stretch, so it's the stronger spring. It's the higher K value. You could even plug in numbers, say 3 newtons over 0.2 meters, and that'll give you 15 newtons per meter. And then with this one, it looks like you could take, what is that, 2.8 newtons over 0.3 meters, which is going to be closer to 10 newtons. I'm not going to do it exactly. Newtons per meter. So the spring B is stronger, has a higher K value. 39. The answer is 1. You have a car horn. This is your classic Doppler effect question. In the Doppler effect, those of you who have me in class will understand the flag. Here's a car coming towards you, and it's emitting, let's say, 500 hertz sound wave. If the car's not driving towards you, if it's just parked there, you're going to hear 500 hertz because there are going to be 500 pulses that hit your ear every second. If this car is moving towards you, each successive pulse has less of a distance to go, because in the time from when you emitted the last pulse to when you emit now, the car has traveled some distance. It doesn't have as far to go as it would have if it was just parked. What that leads to is a perceived higher frequency by the observer. So you're going to hear a higher frequency. Depending how fast it is, tells you how big the Doppler effect is, how big the shift is. So instead of hearing 500 hertz, you might hear 600 hertz. If it goes away from you, the opposite is true. Instead of hearing 500 hertz, you might hear 400 hertz. It's going to be lower. So as it comes towards you, it says it's going away from you, you're going to perceive a lower frequency. It's also going to get quieter as it gets further away, so it's going to decrease in amplitude. The answer is 1. And finally, question 40, the answer is 2. And this is a good time to just talk about projectiles. In this case, you have an airplane, but it doesn't matter. As an object falls, I'm going to use this. Horizontally, it travels at a constant speed. Vertically, it's accelerating. In fact, vertically, it has an acceleration of minus 9.8. In fact, let's make a little table here. We have x things and we have y things. Whenever you have a projectile, in the x direction, that velocity initial and the velocity final equals a constant. In this case, that constant is going to be 100 meters per second. In the y direction, that initial velocity, when it's launched horizontally like this, is 0. When it's launched at an angle, it's something else. You have to get the components. V final equals, who knows, depends. The acceleration in the x direction is 0. The acceleration in the y direction is minus 9.8 meters per second. The distance in the x direction is known as the range, and the distance in the y direction is known as the altitude. The thing that is exactly the same between these two is the time. That really doesn't belong to either. Now, I usually like to use red for the x things and blue for the y things. And I have an expression which is no purple. And what that means is whenever you're using an equation, make sure you don't mix up the x and y things. For example, when you're getting the range, don't use an acceleration of 9.8. It's going to be 0. The question doesn't ask for it, but if we wanted to get the range, that is like a distance. D equals VIT plus 1/2 AT squared, but it's in the x direction. So that's going to be an initial velocity of 100 meters per second. We're told the time was 30 seconds. The A is 0 meters per second squared. It's not 9.8 because it's the x direction. And that would give you a range, in this case, of 3,000 meters. So I talked a lot, but this is YouTube, so you can skip whatever I'm saying. I tried to be as thoughtful and give you as much advice as I could while you're doing this. Let me know if you have any questions. And at least I kept it under an hour.